On this worksheet, we are going to practice learning how to write electron configurations. In order for us to write an electron configuration, we need to know how many electrons are in an element. And so that's why I have the periodic table open over here to lithium. The atomic number of lithium is 3, which means it has 3 electrons. Now, the electron configuration is a description of how these 3 electrons are arranged in the lithium atom. That is also given to us in the quantum numbers. So the quantum numbers are also a description of how the electrons are arranged. Quantum numbers and electron configuration both give us the same information. What we're going to do is start by writing possible quantum numbers, sets of quantum numbers for all 3 of these electrons. So we have 3 electrons. We want to come up with sets of quantum numbers for all 3 of these electrons. When we do this, we usually typically we start by working with the lowest possible energy quantum numbers, meaning that we want the smallest possible values. As you know, the possible values of n are 1 or 2 or 3, etc. And we want to start by choosing the smallest possible value of n. When n is 1, L can only be 0. And when L is 0, M sub L can only be 0. M sub S could either be plus 1/2 or minus 1/2. And in terms of energy, plus 1/2 and minus 1/2 are exactly equal to each other. So when you're choosing M sub S value, you can choose either one, it won't make a difference. Now for electron number 2 can have identical N and L and M sub L values, but we can give it a different M sub S. Remember, any 2 electrons in an atom cannot have identical quantum numbers. So every single electron in an atom has to have something unique about their quantum numbers. Like here we have different M sub S values. Now this is all that we can do with n equals 1. So the next electron needs to go into the n equals 2 energy level. When n equals 2, our possible values of L are either 0 or 1. And remember, we want to focus on the smallest possible numbers. So that means we're going to stick with L equals 0. And when L equals 0, M sub L has to be 0. And then remember, for the M sub S values, it doesn't matter if we choose plus 1/2 or minus 1/2. In terms of energy, they're exactly the same. So these are possible quantum numbers for electron 1, 2, and 3 in the lithium atom. Next, we're going to draw a blank orbital diagram. Alex refers to these as box diagrams. In the blank orbital diagram or the box diagram, we use a box or a line to represent every orbital. An orbital is indicated or given to us by the first 3 quantum numbers. So any electron that has identical quantum number L and M sub L and N, the first 3 quantum numbers are identical, that is going to be represented by, on this diagram, either a single box or a blank line. So it's going to look something like this. We're going to have like an axis to give us the energy. We're going to use either a box or a line. I'm going to use a line. We're going to use a line, and that line is going to be used to represent, in our case, the n equals 1, L equals 0, M sub L equals 0 orbital. So we need one line for these 2 electrons, or one box if we're doing this on Alex, and then we need a second one for this electron right here. And that second one is going to be a little bit higher in energy, like that. Now, the last thing that we want to do is label these lines, or if we were on Alex, label them with boxes, and we label them using our designation, our abbreviation from the quantum numbers. N equals 1, which means we're going to give this a 1, and then L equals 0. L equals 0 is represented as the letter S. For our second box, we have n equals 2, so this is going to be 2, and L equals 0, and when L equals 0, we call that S. Sometimes we write these labels to the side, or sometimes we write them underneath. Doesn't really matter. Now what we're going to do is fill in these orbitals in order of low to high energy. We do that by using arrows to represent the electrons that are occupying each one of these orbitals. So for our 1s, the 1s is being represented by these electrons right here. 2 electrons means that we need to have 2 arrows in this diagram. One of them is going to be pointing up, and the other arrow is going to be pointing down. And this up versus down is what's communicating the two different possible values of m sub s. Now, just to be clear, there isn't any kind of rule that says this is going to be positive 1/2, this is going to be negative 1/2. We just have our electrons pointing in two different directions to show that we have both the possible m sub s values. So for electron number 3, which is in the 2s orbital, there's only one electron in this orbital, which means we only want one arrow. Now, this is all very tedious. Quantum numbers and the diagram, these are both ways of communicating the arrangement of the electrons in this atom. An easier, faster way to do this is to use the electron configuration. In the electron configuration, we start from the bottom, low energy. We write the name of, or the abbreviation for the orbital, 1s. And then we write in superscript the number of electrons that are occupying that orbital. So we write 1s, and then the 2 tells us that we have 2 electrons in that orbital. And then we just keep working our way up. So the next is the 2s, and we have 1 electron in the 2s orbital. 1s2, 2s1. Last question for lithium, is it diamagnetic or paramagnetic? Lithium is paramagnetic, which means that it has at least one unpaired electron. In our case, the unpaired electron is in the 2s orbital. So unpaired would mean all by itself. These are paired electrons. This is an unpaired electron. So now that we've gone through that, we're going to do a pretty similar thing for beryllium. We're going to do the orbital diagram and write the electron configuration for beryllium. Beryllium has just one more electron than lithium. We're not going to write all the possible quantum numbers. We're going to go straight to the orbital diagram. We're going to need all of the spaces that we needed for lithium. We're just going to need to add one more electron. So we have 1, 2, 3, 4 electrons in beryllium. Now you probably noticed that instead of like angling out my orbitals, this time I just stacked them one on top of the other. That's pretty standard notation as well. Alex does move them to the side like this, but a lot of people just stack them directly vertically like that. Now let's write the electron configuration for beryllium. We have our 1s orbital with 2 electrons in it, and we have our 2s orbital with 2 electrons in it. Now we're going to do the same thing for boron, which has 5 electrons. So that means that we need to add a 5th electron to this diagram. Now we cannot put any more than 2 electrons into any given orbital, which means that we're going to need more orbitals than the 1s or the 2s. We're only able to put 4 total electrons in these orbitals right here. So what comes next in terms of energy after the 2s orbital? The 2s orbital is followed by the 2p orbitals, and there are actually 3 2p orbitals. They are all identical to each other in energy. We can see this reflected in the quantum numbers. When n is 2, possible values of L are either 0, that's what's happening in the 2s situation, or 1. When L is 1, we refer to that as the p orbital. When L is 1, our possible values of m sub L are -1, 0, or 1, and those 3 possible values give us 3 possible orbitals that we could work with. For boron, we have a total of 5 electrons. Again, we get that from the periodic table. 1, 2, 3, 4, 5. And for our electron configuration, we have 1s2, 2s2, 2p, 1 electron in the 2p orbital. Okay, so now we are moving on to carbon. Carbon has a total of 6 electrons. We are going to draw a blank orbital diagram with enough empty orbitals. So we just need 1s and 2s, and we need those 2p orbitals as well. And we're going to fill in those 6 electrons in carbon. 1, 2, 3, 4, 5. Now, what do we do with number 6? Because we have some options here. We could put number 6 here, we could put number 6 here, or we could pair it up with this one. We do have a rule called Hund's rule that says that every orbital will get 1 electron before any get 2. So that means that when we're filling up in the 2p spot, we want to put 1 electron in each one of these 2p orbitals before we start pairing any of them up. The electron configuration for carbon is 1s2, 2s2, 2p2. Is carbon diamagnetic or paramagnetic? It's para. Remember, that means that it has unpaired electrons. There is an unpaired electron here, and there's another unpaired electron right here. A paired electron would be 2 electrons occupying the exact same spot in an energy diagram, like that. Draw a diagram and write the electron configuration for nitrogen. Nitrogen has 1 more electron than carbon, so we'll be able to use the same orbital diagram. A total of 7 electrons, 1, 2, 3, 4, 5, 6, 7. The electron configuration is 1s2, 2s2, 2p3. And now we're going to do this for oxygen. We're still going to be able to fit all of those electrons into the 1s, the 2s, and the 2p's. Total of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Remember, every box or every line gets 1 electron before we start pairing any of them up. 1s2, 2s2, 2p has a total of 4 electrons. Now we've got 2 more. Draw the diagram and write the electron configuration for chlorine. Chlorine has 17 electrons, which means we're going to need a lot of lines on this diagram. And I'm not totally sure how many we need, so I'm just going to put a few. I know we're going to need the 1s, the 2s, and all of those 2p orbitals. And we're probably going to need more than that as well, so I'm going to add some more. Next comes the 3s, and then the 3p, and hopefully that's enough. Now, if you're not completely sure about what order the orbitals come in and what they would look like, you can pretty easily find this just by Googling. I'm just going to pull the internet up. If we just Googled something like blank energy diagram. Nope, that's not a good one to do. Order of energy of orbitals. Let's try that. Orbital filling. This is a great one right here. So this is showing for electron configuration, the this Wikipedia thing is showing the order in which the orbitals are filled. So if we're looking at this right here, we could see if we need to go beyond 3p, the next one is going to be 4s, and then after that will be 3d and things like that. And it's possible that we could see some good images that would be helpful for that. There's a lot of these little crisscross diagrams that are helpful to some people. My eyes don't really like to look at those. But these resources are on the internet or in your textbook if you're struggling to know the order of the orbitals. So chlorine, we said, had, let's pull that periodic table back up. Chlorine has 17 electrons, so that means we want to put 17 electrons in these boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Write the electron configuration. We have 1s2, 2s2, 2p6, 3s2, 3p5. And then last but not least, we have potassium. Potassium has 19 electrons, which means we're going to need 2 more electrons than what we just did for chlorine. So we will need to add that next orbital And if you remember from that little Wikipedia paragraph, the next orbital was 4s. So after the 3 p's, the next one that we're going to do is 4s. And we need 19 electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1.